So welcome. Today I'm going to be going into an introduction to quantum Monte Carlo methods, focusing on really the essentials for production research calculations with real space quantum Monte Carlo methods for molecules and materials. So it's the foundations for the hands-on and practical applications of these methods that we'll be doing in the subsequent sessions of this summer school. As before, I'm Paul Kent from Oak Ridge National Lab, and all the materials for this summer school, including a copy of these slides, are on this GitHub site. So a brief outline of this presentation. I'm going to remind us a little bit about why we're here, talk about the electronic structure problem, and then we'll move into first variational approaches to solving the Schrodinger equation with variational Monte Carlo, talk about wavefunction optimization, so improving the trial wave function needed by those methods, and then move on to the more accurate but also more expensive diffusion quantum Monte Carlo method. And this is the real workhorse for the calculations on larger molecules and materials. I'm also going to touch on some practicalities and give some sort of rough guides to the sort of numbers as regards statistics and time steps you might see in these calculations, just so you can get a feel for settings you might want to use in your own calculations. And then after this session coming up, we have some still important technical topics. For example, on Tuesday, we'll be discussing shooter potentials, which are very much needed for real-world calculations on larger systems where all-electron calculations wouldn't be feasible, statistical analysis, and also computational workflows. So necessarily, I'm giving a boiled down and concise presentation of the methods of both Variational Monte Carlo and Diffusion Quantum Monte Carlo and Wavefunction Optimization in this talk. Where can you go to find out more information? And we're fortunate in that there's a good number of review papers and even books published recently that are actually very approachable and good places to go for more info, more in-depth information. So I'm showing here two review articles and a book. First, I would point to is this review article in the Reviews of Modern Physics. That's this first reference here, published by Matthew Fulks and co-authors back in 2001. And this has turned out to be a classic and very easy to read review on not only quantum Monte Carlo simulations of solids, which is the title, but also I think it's approachable enough that it can be applied to molecules as well. So that's a very friendly review paper. Of course, the problem is that really we need to write a new one of these fairly shortly because it doesn't have any of the new methods that have been invented since 2001 in there, and there's actually quite a few. I'm going to touch on quite a few in this presentation. Still a good starting point. There's a good number of review articles in the last decade or so. I'm showing one here in Chemical Reviews by Mateusz Dubecki, which, although in the title it says non-covalent interactions by quantum Monte Carlo, very much focusing on van der Waals, it also has a very approachable introduction to diffusion Monte Carlo and shooter potentials and even the treatment of periodicity for example. And so that's one that I would also recommend. There's also a number of books that are being published. This is a more technical one, Quantum Monte Carlo Approaches for Correlated Systems by Becker and Sorella. Maybe your library has that. Also, another way into this field to get references is to look at the citation papers for the different QMC codes that are out there, as they usually review recent work. So if we look what we did for QMCPACK, we published our first review article a citation paper back in 2018, and then did a follow-up with some of the advances in 2020. Now, these are both open access, so you don't need a subscription to the journal. And I'd point out that this issue of JChem-Phys is a special issue, and there's quite a few other papers by the authors of other electronic structure codes, including quantum Monte Carlo codes in there, so that's a good place to browse. I also know that out for review at the moment, and but up on the archive here, with the authors of 10 other QMC codes, we've done a reproducibility study for at least in the case of one reaction. So this paper has citations to lots of codes, and you can dig back through those to find more details of the algorithms and underlying theory. And just a little bit of a spoiler, we do indeed find that in the case of the reaction studied, if enough care is taken, happily the codes agree. That's important to do. So, why are we here? What's the important problem we're trying to solve? Well, it's the electronic structure problem. And I think most of us are here for high quality first principles, so ab initio solutions of the Schrodinger equation for non-trivial materials and molecular systems. And of course, this is what I referred to in the previous presentation. This is a challenging equation to solve, and Paul Dirac noted that yes, we know the equations for much of physics and chemistry, but we need approximate methods for solving them. But of course, we don't just need approximate methods, we need the methods to be highly accurate, or at least sufficiently accurate for our science. Ideally, whatever approximations there are can be tested and made smaller. And importantly, and this is one of the advantages of quantum Monte Carlo, we would like the methods to be applicable to a broad variety of systems. So not only molecules or solids, but both molecules and solids, metals and insulators, and of course, more complex interfaces and nanostructures and catalytic systems, for example. So that's part of our motivation behind quantum Monte Carlo. Let's think now a little bit about the maths behind the Schrodinger equation and what's going to be challenging to solve. And here we're going to be focusing on the zero temperature Schrodinger equation and in the Born-Oppenheimer approximation, which is already hard enough to solve. But of course, solving for time-dependent properties is also very important, right? But that's a whole extension from all of this. So what do we have? Well, I think we'll probably all recognize these equations. So we have, H psi equals E psi. So apply the Hamiltonian to the wave function as the energy times the wave function. What is in the Hamiltonian? Well, of course, we have the kinetic energy of the electrons. We have a Coulomb term. So this is an electron ion term. I think I use the suffix, I use the terminology d alpha for the positions of atoms when I wrote this. And then the source of a lot of the difficulty, but also the interesting properties in the materials and molecules, the Coulomb interaction between all the electrons, which is, of course, very long-ranged. And that's not the only part that makes this difficult, of course. To ensure that we have a fermionic solution of this equation, so to properly represent electrons, there's the very important antisymmetry condition. So if we write the many-body wave function, which is of course a function of all n electron positions, if we interchange any two electron positions, then the wave function must change sign. And this combination of properties is what makes the Schrodinger equation hard to solve. And it's actually been shown in a few cases that this is a non-deterministic non-polynomial time hard problem. So we won't be able to find a polynomial scaling solution to this problem if we seek the exact answer. It's going to be combinatoric or exponential in some way if we want to find the exact solution. Of course, for our science, what we really need is a way to sort of sneak up and approach towards the exact solution until the point where we've got sufficient accuracy in whatever properties we're interested in. Still a very challenging task. So in this presentation, I'm really going to be talking about two main quantum Monte Carlo methods, variational Monte Carlo and diffusion Monte Carlo. And I thought it'd be good to give this sort of initial perspective of how they relate to each other. So this is a little hand wavy, but we've got a sketch here. On this graph, the y-axis is accuracy, and at the top here, this is an exact solution. And on the x-axis, we have computational cost. So let's look first at variational Monte Carlo. And this starting point is for a single determinant trial wave function. So where the fermionic part of the trial wave function is just a single determinant. That's the simplest wave function that satisfies the symmetry conditions and is actually, but still nevertheless, a very good starting point for research calculations. So there's research calculations at big journals currently under review using this form. So this method has some initial, modest computational cost or reasonable computational cost and some reasonable accuracy, but we're not at the top yet. So perhaps it captures 60, 70% of the correlation energy in the system. And there are, of course, ways to improve this trial wave function, moving up towards more exact result or less inexact results, but more computational cost, such as by having more determinants. Now, the second method, and this is the real workhorse in chemistry and materials, is diffusion Monte Carlo, where using the same determinant, the same wave function as down here, it's initially much more accurate at the trade-off of more computational cost. And of course, we can also increase it using similar methods to the VMC to the point of hopefully sufficient accuracy for our science. Of course, one complication is that for any real research project, we've got some sort of fixed amount of patients or computer budget, and so we're going to need to plan out, do we want to do a lot of calculations with this sort of standard form of the method or really work to improving the results? Now, I also want to point out that there's quite a few review papers I see where people essentially say that there is no exact solution to these methods and that to the Schrodinger equation, and that's not quite true because these methods do exist on the books. The issue is that they're just not practical enough. So one example is full configuration interaction, where if one uses a large enough basis set, that will tend towards a complete representation of that n-electron wave function with all the right symmetries. The issue is that this is an explicitly exponential or combinatorial approach, so it runs out of steam before we can look at a system of decent complexity. And then another one that I know a lot of you think of is actually a quantum Monte Carlo method, and I put the reference to it here. So Seppeli and Alder in 1980 have their very famous study of the homogeneous electron gas using release node quantum Monte Carlo. And this, of course, is the data that was parameterized in the local density approximation to form the first really widely successful density functional approximation. And the thing about release node quantum Monte Carlo is that it is also formally exact, but again, a little bit like full CI, but for different reasons. It's impractically exponentially scaling. So it is too expensive to apply to, I think, much more than a beryllium atom, even today. So it works for some model systems, but not applicable to ab initio systems, unfortunately. So given that setting of the scene, let's now talk about variational approaches to tackling this problem. And what we're going to use here is the variational principle of quantum mechanics, which should all be familiar to us from some of our early quantum mechanics lessons. And essentially what we know is that if we evaluate the energy of any trial wave function, basically by definition, it has to be equal to or above the ground state energy. So we take a trial wave function, psi t, do the expectation value of the Hamiltonian and normalize it. This gives us an energy, and that energy must be above or equal to the ground state energy E0. And since we're exploiting this should be immediately obvious that we're going to need accurate trial wave functions for this and good methods to further improve them. Now, at this point, we don't have to do Monte Carlo, but if we think about doing this with these integrals with numerical integration, if we have one electron, that's a three-dimensional integral, two electrons, that's a six-dimensional integral, 100 electrons, that's a 300-dimensional integral. And so if there's any power law cost to doing the numerical integration, as indeed there is, this is going to become wildly impractical beyond a few electrons. What we can do, though, is rewrite this equation a little bit by inserting and dividing by another psi t here and put it into a form that is suitable essentially for textbook important samples Monte Carlo. And so that's shown here. So we've added and divided by a psi t. And so what is this first term? We've got the modulus squared of the trial wave function, so it's positive definite. And this has been appropriately normalized, so this is going to integrate to 1. So in other words, this is a probability density function that we can use in textbook Monte Carlo. Now, what is this other term? This term is actually a scalar. It is, so the Hamiltonian applied on the wave function divided by the wave function is an energy, and it is the local energy. That's a term that occurs widely in the quantum Monte Carlo literature. And so if we evaluate the local energy over this probability density, we can do this integral and get the energy of this trial wave function. So that's essentially what's done in variational Monte Carlo. I won't go through the derivation here, but it's essentially the classic Metropolis algorithm back from the original paper in 1953 in JChem Phys. And essentially what one does is take an initial set of electron positions, have some scheme to propose moves to them, and then if the wave function squared is larger, where you've just proposed moving to, you're going to accept that move. If it's smaller, well, you still accept that move some of the time based on a random factor and a ratio of the squares of the wave function. And so that looks a little bit like this. So for every Monte Carlo step, we're going to work through every electron, and it's most efficient to do this one electron at a time. We have some scheme for proposing moving electrons, so some transition probability, and then we have an acceptance probability that I just said. So if this is the transition probability is the same both ways, you can see that's immediately what I said. And if the wave function squared is larger, we're always going to be accepting. Otherwise, we're going to accept with some probability between naught and that ratio squared. How do we generate these new configurations? Well, normally there's a normal or Gaussian distribution to the proposed moves whose width is proportional to a time step, quote unquote, but it's really the width of the distribution, how large the steps are going to be on average. And so just to note here, and this is a foreshadowing of the issues in diffusion quantum Monte Carlo, the acceptance ratio here, we might aim for 50% plus or minus, and that turns out to be quite efficient. One can do efficiency studies, but the thing to note here is that the acceptance rate only affects the efficiency of the scheme. So there's no approximations here. This is just about the efficiency. The challenge is getting a good enough trial wave function. And just to say a little bit about what the codes do, of course, no one here needs to implement that unless you're super motivated, because there's many codes, including QMCPACK, that implement this. We have some initial generation of electron positions. We're going to propose moves. We evaluate the wave functions at new positions. We have a Metropolis accept reject. And if we accept, we do some bookkeeping to actually update the position. And then we compute the local energy and any other properties that are of interest to us. And the thing to note here is that even if we've rejected the step, we compute that and accumulate it, because if we're in a very likely position, obviously there should be more weight to that property. So this is needed to get the correct results. And one then does this potentially thousands or millions of times, and then does statistical analysis on the values that we noted down at this step. So what sort of things are we going to measure? Well, in this summer school, we're very much focusing on the energies and trial wave functions, since they're really the foundation for all other quantum Monte Carlo calculations and measuring of other properties. You need good trial wave functions and their consequent good energies before looking more broadly. So what are we going to measure? Well, we're going to measure the variational Monte Carlo energy, which is just the average local energy throughout the run. And this is needed to compute formation enthalpies, for example, total energies. And we also look at the variance, the statistical distribution of those local energies, because this actually turns out to be a measure of the quality of the trial wave function, as I'll go to in a minute. Now, a note here on one very important difference between doing Monte Carlo and conventional self-consistent field calculations. The Monte Carlo error bar converges as 1 over the square root of the number of samples. And it does this independent of dimensionality, which is a little bit of the magic of Monte Carlo. But it's important to think about what that means in terms of convergence rate. And I've tried to sort of sketch this here, right? So if we have an initial computed error bar of plus or minus 2, let's say, based on 100 steps, and we now take 400 steps, well, the error bar will reduce by the square root of 4, which is 2, so now our error bar is 1, right, for 4 times the amount of work. And so if we want to reduce an error bar by 10 times, that's going to cost 100 times more compute power. That's just the scaling properties of Metropolis, of Monte Carlo. So it's very important to plan calculations, and one can, of course, do a short run to see what the error bar is. This is quite different from a self-consistent field calculation where if you try and converge them by an additional order of magnitude, for example, when you're doing, say, density functional theory, that might only cost you 10%. In Monte Carlo methods, that extra 10x will cost you 100x. So it's important to plan how accurately do you need to know the results. Now, a note here on the trial wave functions that are being used, and we're going to have a lot more of this in the following session. So I'm putting here the general case, which is more general than we're going to need to use. But let me outline a little bit of the landscape, as there's quite a few choices that you'll see people make in the literature. So the trial wave function, psi needs to be fermionic. And so there's a fermionic part, which is usually one determinant, which could be a Hartree-Fock determinant, for example. And we could stop there, but we could also put in a CI expansion, as shown here. So CI singles doubles, and so on, depending on what techniques are available to us for the system that we're trying to study. So this is the fermionic part. And then we put in a correlation part called the Jastrow factor. And this is a function of inter-electron and electron-ion distances designed to build in some physics. And let me talk a little bit more about this right now before going back to the determinants. So one thing that's done here is to build in some physics that is very slow to be picked up by determinants. So in a many-body wave function, one property that's very important to have is the electron-electron cusp. So the shape of the wave function when electrons approach each other. And that can be put in more or less directly in the Jastrow factor and converges very slowly in traditional CI and CAS-SCF schemes, for example. What else is in this Jastrow factor? Well, normally it's there's some one-body terms, so electron-ion terms, two-body terms, so electron-electron terms, and maybe some more involved terms involving multiple ions and electrons. And these are going to be parameterized in terms of the number of coefficients, and we're going to optimize those to find the best possible choice. There's quite a few varieties used in the literature, and I put a reference here to a paper developing a very general wave function. And importantly, there's a lot of consideration and discussion of the different terms one might want to have in different cases, and done by the Casino group. Fortunately for most molecular and solid state systems, there's essentially one sort of standard choice that we'll be pointing out, just some very simple 1, 2, and 3 body terms that works very well. Now, what about this determinantal part, this where the fermionic nature is enforced? Well, the starting point that we're going to recommend for everybody and is used widely in research calculations is just a single determinant of orbitals from the best density functional calculation that we can do. So perhaps a hybrid calculation or a DFT plus U scan. That has the right fermionic symmetries and turns out to work very well. Or alternatively, we could do the best quantum chemical calculation that we can do. And that gets us a starting point. If we want to work towards increasing accuracy, or there's a particular tricky system, we might do CI or CAS-SCF, or even just write down the determinant expansion by hand and rely on the optimization scheme to find the coefficients. Because the reason we like to start from the best available quantum chemical result is that, of course, that's going to save us time. That's going to require less effort on the quantum Monte Carlo. What do those look like? Well, I've plotted here the examples of the up spin, the up down, and same spin electron pieces grabbed from a particular run of the carbon-24 fullerene in QMCPACK shown here. That's the purple and the green. So this is value of the radial part of those functions against distance. And we see they have some initial value and they trend smoothly towards 0 here by about 8 atomic units. And then if we look at an electron ion term for the same system, this is all found through automatic optimization. We see sort of a larger value also trending towards 0, about the same distance. And we see maybe there's a bit of structure in this because of the different because of the atomic configuration of C24. And so in this example, this was using the standard Jastrows used by QMCPACK we'll be pointing you to, which is simply actually a series of points in real space for these, which it then splines through. And just to begin giving some sort of numbers that you might want to see in terms of sort of parameter counts here, there was 1 every atomic unit in these spline functions. So there's about 30 parameters here in that case. And one thing we do want to see is, since there's a cutoff distance for these functions, we want to see that they go nice and smoothly towards 0 at the end. That's a mark of a good optimization, and all the correlations being captured before that cutoff. So far we've got enough to do variational Monte Carlo, but now we need to find the coefficients in the Jastrow function and potentially more. So I'm going to show 2 schemes here. First, the variance minimization approach, which I think was the first really successful, widely used approach, and then the breakthrough energy minimization or linear method approach, which really let people target improving energies. And in a fairly robust manner. So let me talk first about the process we need to go through here and variance minimization. It's quite easy to see how this one might work. So what are the properties of this wave function that we can potentially exploit for in an optimization process? So first of all, of course, we have the energy of the wave function, which is higher or equal to some unknown ground state energy. So of course we can just have an optimizer and try and make the energy smaller. And that turns out to be quite challenging numerically. We'll get into that in a moment. But of course, another thing we know is related to the variance of the wave function. And in particular, the variance is positive definite, and it will go to 0 if we have an exact eigenstate, including the trial wave function. And one can see that here. So this is a standard statistical approach for the variance of a quantity. So the sort of the spread away from the mean squared summed over the number of samples. And if we have an exact trial wave function and we compute h psi over psi, well, that will be the ground state energy, and that's going to be constant everywhere. So this is a constant, E0, if we have the exact ground state wave function. This is E0, averaged again. So this term in the brackets is 0 in the case of the ground state wave function. So this can actually be used as a measure of wave function quality. And there's exercises one can do, putting in an expansion, a basis set expansion of energy ordered eigenstates in this to see this in more details. But we've got something that we can optimize here. And this was used very much in the 90s and early 2000s to form a lot of materials and molecular studies. And essentially, and it includes a couple of tricks that are still used today. So how does one do this? Well, one uses a Newton-like optimizer to update the parameters p or coefficients in the wave function. And since we can already evaluate the energy invariance of the wave function, in principle, we have a scheme that we could implement already, but there's a few tricks that are used to make this efficient. So for example, instead of doing completely independent quantum Monte Carlo calculations for a new set of parameters p prime proposed by the optimizer, there's this trick to recompute, to reweight the existing probability distribution you have to get the new energies. And this also means that the new energies are going to be statistically correlated with the old ones, and that improves the efficiency of the approach. So this is the sort of trick we're looking for in many Monte Carlo methods. But one uses that to avoid doing completely independent QMC runs, computes the new energies, and then you have some decision scheme in a standard jump down a hole or line following optimizer. And then you repeat this multiple times in order to get the best wave function. So lower energies and importantly, lower variances. If the wave function is simple enough, there's actually a number of tricks that can be done to make this even more efficient. And actually, as part of this study, as part of this work proposing such a scheme, there's a nice plot here showing something that you might also be thinking about, which is, okay, how many statistical samples are we going to need to make this optimization approach work? Is it practical? So this is from a study of an all-electron neon atom. And what's plotted here is not the energy on the y-axis, but the variance, so lower is better. And then this is one of the parameters, so alpha 1 that's in the Jastrow function here. And what we see here is the computed variance against changes in that parameter done with different numbers of sampled configurations in this particular study. And so we see, well, if we take 10 at random, we don't get this minimum in anywhere close to the right spot. But maybe by 1,000 configurations, that's a green line, we're starting to get close to the shape here that's seen if we have a very large number of configurations. So the point I'm trying to make here is actually even for this a neon atom system, thousands of configurations were needed in the optimization. And of course, fortunately for neon, there's not too many electrons, so this is very affordable. One other thing to note here is that even with the optimum value, the variance is not 0. It's, was it 25 or 30 or so on this scale. So this is a successful method, but it turns out to be, in practice, very challenging to make substantial improvements to both the energy and variance of particularly complex wave functions with a lot of degrees of freedom in. So for example, if we wrote down a configuration interaction expansion with a lot of determinants, that tends to be too hard for the standard variance minimization scheme to make much progress on, unfortunately. Fortunately, there is the breakthrough method due to Cyrus Umrigar and co-workers, which is often termed energy minimization because it's a scheme that let direct minimization really work in practice, as I'm going to be showing. But really, it's the linear method because it's based around a linear expansion of the trial wave functions. So this was a real breakthrough step and applied on a couple of dimer systems initially, and I'm going to talk through those results now. And of course, This is all implemented in the QMC code, but it's important to know some of the backgrounds and the differences behind these approaches. So what was done in this scheme is you take your initial wave function at some initial set of parameters, and these are the electron configurations, and you sort of do a linear expansion of this wave function. Obviously, you need access to the derivatives of the wave function with respect to the parameters, and we've now got these potential changes in parameters delta pi. So far we haven't done anything. But then the realization is, well, you can write down very much like a Schrodinger-like equation, which is very similar to like the generalized Hartree-Fock or SEF equations you might see in quantum chemistry, and solve that for the lowest eigenstate to get the more optimum changes in parameters, and then feed that into an updated wave function. So that was what was done in this scheme. And then not shown here, there's also some numerical tricks, very smart numerical tricks to help stabilize this diagonalization and help the diagonalizer to really robustly find the ground state eigenvector. So what do they show? Well, I hope this isn't too small, but on the y-axis here, this is energy against iteration for carbon-2, which is actually quite a difficult system. And we see the initial energy here in the first cycle, and we see a big reduction in energy and subsequent convergence. That's actually shown in the inset. So you start to see the energy bounce up, indicating that your results are now being governed by statistics, and there'd probably be more bouncing if we kept running. Note that the statistics aren't kept constant through this run. After getting reasonably converged, they increase the number of configurations, as says here in the caption, from 10,000 to 400,000. And that's something typical you have to do in any wavefunction optimization, because to resolve small changes in the parameters, you're going to need many more samples, many more configurations than you need to resolve large changes in the parameters. They also showed some very interesting comparisons between Variational Monte Carlo and Diffusion Monte Carlo. So I'm going to talk to this graph on the right. So this is energy against number of determinants. The red is Variational Monte Carlo. So the first is where you just optimize the Jastrow function, and we get this plot here. So the coefficients and the configuration state functions, or the determinants, are coming from a self-consistent field calculation, and we have this particular accuracy. Now, if you could use this new scheme to optimize the determinant coefficients, you get this curve, a significant improvement in the energy, and we formally know that lower is better because of the variational principle. And then finally, if you optimize the orbitals, or the coefficients in the basis expansions describing those orbitals, we get a lower energy still. So I think this was the first time this huge improvement had been shown, and they got about 0.02 Hartree with this method with the optimization. So that's a big improvement. Now let's look at the diffusion Monte Carlo results. Now I haven't described this method yet, but I'll just say it's more accurate and more expensive. And for example, we see here that already out of the gate with the same wave function, it gets a much lower energy than the VMC. But now if we only have optimized the Jastrow function and we take the determinant values from a self-consistent field calculation, I think it was CAS-SEF, sorry, it's CAS, we get this progression here. And the thing to note is that if we look where the best VMC result ended up, we see actually that we were able to make a better trial wave function through VMC than DMC, just by working hard enough at the trial wave function. And that's something I tried to hint at when I gave that sort of initial overview of VMC and DMC. Of course, if we go through the same process and optimize everything, we get lower energies still. Notice that in VMC, we got about 0.02, but in DMC, which can already squeeze more out of the trial wave function, it only got about 0.01. So DMC is more efficient at recovering correlation energy than a VMC. So this is a very important step in the field. I should mention there are a couple of snags still with this method. So it's not perfect. It can be a little brittle, and you'll start to see energies go up if you don't have enough samples. And compared to some other schemes, it uses quite a bit more memory. And that's not going to be relevant for the systems that we're running, but as one starts to do tens of thousands of parameters, that can start to be a concern. Now, a little practical note, you might be wondering, well, how now do we run this on our different computers, on our computers we have access to? And this turns out to be quite a straightforward mapping. What we're going to do in Variational Monte Carlo and to generate the samples that we're going to use in the optimization is we just put one Walker, that's the colloquial term for one set of electron positions, or really it's a Markov chain in the Monte Carlo on each CPU core. I'll note that if we had GPUs here, we'd have to put thousands, and we'll be going into that difference in a couple of weeks' time. So that's sort of shown here. We have this sort of noisy plot measuring the energies in the Monte Carlo for each CPU. And then one thing that I think actually every QMC code does is subdivide this run. So we do lots of steps in the Monte Carlo, but then break it up into blocks and only write out summary statistical results every block. And this is a convenience and an efficiency measure because it means, the codes are only writing data every block, and they're not going to be spending too much time doing I/O. So that's a little bit of the nomenclature. So fortunately, VMC maps really well onto our current hardware. So a little review now on the workflow that we'll be following. So first of all, we've got to generate the determinantal or fermionic part of the trial wave function. And we're going to do this using, our preferred best available DFT or quantum chemical method. And we'll use as large a basis set as we can for that. I also wish to emphasize that the standard recipe of using a single determinant does work very well. So that's where we're going to be starting. We then need to add that correlation function, the Jastrow factor, and then optimize it. And for most work, just optimizing the Jastrow function is enough, but increasingly more of the coefficients are being optimized, and for systems much more complex than the C2 that I just showed you. And then one does a final longer production VMC run, potentially computing not only the energy, but any other properties that you're interested in measuring. Of course, we don't need to measure them when doing the trial wave function optimization. Of course, the first time one tackles any new system or composition, it's important to choose a time step and then try a few different Jastrow functions. So for example, we might want to test different cutoffs, spatial cutoffs on the Jastrow function to see what is most efficient. Because if we can, for example, avoid having too many quote unquote coefficients, that will make the optimization in turn more efficient. Let me talk now through some more VMC calculations. And these results are from a follow-up done by authors of the first paper, by Sarah Simmergar and co-workers. It's always nice when there's longer papers and follow-ups on new methods. And this is more data on C2, but now looking at binding curves. And for anyone who perhaps hasn't computed them, it can actually be quite a bit of work to get the whole shape of the binding curve and the minima, and of course, there's the shape right at the bottom, not just over the whole dissociation. So this first plot here on the left is for single determinant wave functions. And these points here, well, they're Hartree-Fock. So not surprisingly, it's very high compared to this Morse potential plot from, I believe it's experimental data. We see now variational Monte Carlo, which notice does get about the right position for the minimum, so the bond length, but is still missing some energy, and diffusion Monte Carlo improves, but there's still a bit further to go. Now, if we do a certain level of multi-determinant wave functions, and of course they could have kept adding in this study to improve the accuracy further, but in the size that they did here, we see that the multi-configurational SCF calculation has improved substantially. But also the VMC is now very good. It's actually, I think, better than the original diffusion Monte Carlo results from one determinant, and the diffusion Monte Carlo result is now very accurate and very close to the Morse plot. This paper also includes some comparisons with a range of other dimers. And this one down here in blue, so this is the error in the well depth, error in the binding energies, effectively. We see that if we go through the most complex version of this scheme with the most flexibility in the wave function, sure enough, the most accurate results are obtained, and they're very good. And the more simple wave function one uses, obviously the poorer that well depth is. So there are some systematic trends in the accuracies here, as one would expect. Of course, there's much more sophisticated things one can do in Variational Monte Carlo once one has the trial wave function. So I want to point to two results here. So this first is a study which I think is very much undercited, looking at pairing of carriers in the superconductor's iron selenide. And what was done here was to build a very sophisticated wave function up to about 10,000 parameters or coefficients, and then go through a number of steps to analyze what the pairing would be, what the symmetry would be in this superconductor. And notice while this was a challenging calculation at the time, we're now 10 years removed. So this sort of thing is much more accessible. Similarly, you can look at distribution functions and correlation functions. Again, this is something that was done a good while ago and is now very accessible. So this is the G of R comma R primed in silicon plotted standing on a bond. And so we see, there's a big hole here around our initial electron, and we have to go a little bit of distance in order to find another one. And there's also some structure here. And of course, this understanding could be used to build other electronic structure theories, for example. Now, before opening up to questions, let me try and summarize some of the advantages and key disadvantages of Variational Monte Carlo. So first of all, the big advantage is that we can put in essentially any form of trial wave function and really anything that we can imagine motivated by, for example, particular physics or chemistry, certain pairing. We could use a very sophisticated quantum chemical result and further change it. And we're not restricted by the ease of doing numerical integration over that wave function. We only need to be able to compute the value of the wave function and its derivatives at that particular point. So that is much easier for the Monte Carlo if you have lots of correlations between electrons. Since we have the trial wave function, in principle, one can compute any observable. I just showed a couple of examples of those. And then importantly, the Monte Carlo is very, very simple, right? It's essentially textbook Monte Carlo, and there's no error introduced at this stage. So this is the time step, but that just affects efficiency. And I will note that with determinants, the method is nominally cubic scaling with system size in particle count. And that's quite low compared to some of the other many-body approaches that are on the market. Now, what about the disadvantages? And you'll see actually it's the same as the advantage at the top level. So the disadvantage is, of course, that we've got to put in a trial wave function of our own choosing. And of course, yes, through the variational principle, we can put in different candidate trial wave functions and take the best one. But if we're not imaginative enough, we could miss some physics. So the pairing, for example, from the example I just showed. And then in addition, if there isn't quite enough flexibility there, one problem that one can run into, or at least probably worry about, is whether there are consistent errors between different systems of different compositions, for example. Because often we care about the relative energy or relative difference in properties, let's say a dipole moment between two different systems. And we would like to have good error cancellation, as with all many other electronic structure schemes. In contrast, of course, thinking the other way, if we throw in a wave function form with just a huge number of parameters or coefficients in it, that might be very challenging to optimize reliably. And to be honest here, this is the part of quantum Monte Carlo that's not yet fully automated and push button. The VMC will always work. The diffusion Monte Carlo, it's very robust, although not perfect, but the optimization needs a bit more hands-on at this point. So obviously lots of people are working on that, and there's inspiration being taken from machine learning. And I think there's going to be some big improvements shortly in that area, but still not yet fully automated, so some hand-holding can be needed. One thing to note here, just so I don't make sure I mention it, all quantum Monte Carlo methods working in real space, when one looks at periodic materials, so models of real materials, one needs to perform finite size scaling. So one needs to do a calculation with quite a few atoms and electrons in order to be able to extrapolate to the infinite limit. And so that means even if one is looking at bulk silicon or carbon diamond or iron oxide, you can't do the one, two, or four atom primitive cell. You may have to do several hundred atoms. So that means the cost can be quite high. So we'll now move on to the topic of diffusion Monte Carlo. So the more accurate but more expensive workhorse technique of real space quantum Monte Carlo, before going on to some practicalities. So how does diffusion quantum Monte Carlo work? Well, it's from a family of so-called projector quantum Monte Carlo methods, and instead of solving the time-independent Schrodinger equation, they're based around at least an analysis of, or at least inspired by, the time-dependent Schrodinger equation and the evolution of wave functions well, not just time, but imaginary time. And the realization is shown here. So if we write down the imaginary time Schrodinger equation, then we have, d psi by dt equals minus h psi. And the thing is, if we insert a set of energy organized eigenstates and evolve them in time, what will happen is that this, of course, being a partial differential equation we all know how to solve, this is just being just an exponential, while the most high energy states are going to drop out most quickly, and then eventually leaving us with just the ground state. So the excited states drop out in this scheme, leaving us with or projecting the ground state wave function. So this is a way of giving a systematic improvement over some input trial wave function. And that's shown here from a study of homogeneous electron gas. This is the energy against imaginary time propagation in this particular scheme. So yes, we get continuous lower energies, and eventually this should stabilize. So how does one end up with diffusion quantum Monte Carlo? And I'm going to spare everyone the full derivation and just talk about a few highlights of the key features and steps in the derivation of the method. All the review papers that I pointed to, as well as the books, have got the derivation of this scheme for diffusion quantum Monte Carlo, but that would take a few pages to do here, which I think would be a bit too much for this presentation. But what are the key points? Well, first, and one of the most important points, is that instead of working with just the trial wave function, psi t, which we're going to feed in from, say, Variational Monte Carlo, or the desired ground state wave function here, this phi, we work in terms of this product. So some function of electron positions or configurations against time. And notice that this is not psi t squared or phi squared. So this is not an easy to work with probability distribution like we had in Variational Monte Carlo. Then one considers the time evolution of this function by applying the imaginary time Schrodinger equation. And the way this is done is that we consider an ensemble of walkers to represent this function. So we have a set of walkers, and obviously we have delta functions at their positions, but if we have enough of them, we'll get a good representation of this function. And then If we skip a couple of pages of derivation and do a Trotter decomposition that we'll come to in a moment, we end up with some equations that look like this for the time evolution of this function. So the time evolution is something that has a drift term, a diffusion term, and a growth or decay term, where if the local energy with respect to the trial wave function is lower than some reference energy we've had to insert, we'll have a growth multiplying by this function. If it's above, we'll get a decay. So drift, diffusion, and normalization, or growth and decay. Now, to get to this point, we had to do a Trotter decomposition, and we made an approximation. And that is the accuracy of this scheme is to order tau squared, where tau is the time step. So better than linear, but not higher power. And one thing I want to flag up here immediately is that because of this additional discretization that's come in and the need to have a smaller time step, and to keep this approximation small, the typical acceptance ratio you'll see in the diffusion quantum Monte Carlo calculation is going to be 99% or higher. I can't recall seeing a published quality calculation where it's 60% or something like that, because the error would simply be too large in general systems. One thing to note here is, okay, this may look a little bit complicated, but when one puts in the trial wave function, it turns out that nearly all of the terms are ones we already have in our variational quantum Monte Carlo code. We just need to have this variational population, this varying population of walkers. So once one has VMC implemented, DMC is actually not too much additional work. Now we come to really the most important approximation in fixed node diffusion quantum Monte Carlo, because if we were to just evolve the sum input wave function with the equations on the last slide, we wouldn't end up with a fermionic solution. We would have a bosonic solution, and that's of course the wrong one. That's not an electronic wave function. And so the way that is solved is via the fixed node approximation. I think this is really the most famous approximation in diffusion Monte Carlo. And the realization of what is done to ensure a fermionic solution is to adopt the nodes or the zeros of the trial wave function. And so best to enforce that this projected diffusion Monte Carlo wave function has the same zeros or nodes as the trial wave function. So in practice, that means you reject moves that would cause a change in sign in the wave function. And this means that we then get a fermionic solution. And fortunately, it turns out that this scheme is not just some arbitrary approximation. It is a scheme that is properly variational in the energy. And so we could immediately think about setting an optimization scheme around this to improve the nodes or the zeros. Now, what does these surfaces look like? Well, of course, they're 3n-1 dimensional surfaces, so quite difficult to show in general. This is an example for a 2D homogeneous electron gas, and what's been done is to freeze all the electrons but one and just drag them around, and this is the zero shown here. So we have this complex shape for the nodes in this particular system. Now, you might also be wondering, well, now, does it matter where we start and initially put our electrons? Does it matter in which nodal pocket, as they would be described, that they start out in? Unfortunately, that's not the case. There's something called the tiling theorem that says the ground state can only have one type of nodal pocket. So it doesn't matter where you start. In other words, you'll get the same result independently of the starting configurations. So these are very important properties of diffusion Monte Carlo. The most important one from a practical perspective is that when we adopt the fixed node approximation, which every calculation we do is going to, we pick up an error that's variational in the energy. And then as the trial wave function gets better, but importantly, as the nodes of the trial wave function get better, this error goes down. And then fortunately, the single determinant wave functions that I've been suggesting as sort of like the standard recipe in the field, fortunately, they're a very, very good starting point. Let me show what this looks like in practice. And I think a lot of people who give sort of conference presentations on diffusion Monte Carlo results reuse this figure. This is from the Reviews of Modern Physics paper. Let me talk about what happens. So our diffusion Monte Carlo algorithm has mapped onto a set of walkers that are going to evolve in time. And periodically, we're going to remove or kill a walker where it's in an unfavorable position, and ones that are in more favorable locations, so lower potential, they will multiply. You can also use weights on these walkers instead of having integer changes to the walker count. So in this example, we have some simple potential. So lower it's better here. We have some initial positions of walkers. These are these dots. And they're going to evolve in time or steps. And they're going to move around. And then we see walkers that are in the high potential position might get killed, whereas those that are in the more favorable might multiply. And that this then means that over time, we're going to have more walkers in more favorable positions, and hence project out to the ground state and ground state properties. So to note here, because of the fixed node approximation, it's going to be the nodes that determine the final energy we get, but we are still going to care about the overall trial wave function because that's going to affect the efficiency. So that was all a discussion of diffusion Monte Carlo in the abstract. What now about diffusion Monte Carlo in the real world? How does it compare? And I've got two examples here, this smaller one and then a larger one. So this is a result from a published calculation done by Ilka Kalanpa, and the data for this paper is all published, accessible online, and that includes the input files and the output files. And so this is a plot of one of the diffusion Monte Carlo runs that was done for bulk vanadium, so a challenging correlated oxide. And this, if I've done the counting correctly, I think it's a 48 atom cell. The initial wave function is a single determinant from dft plus u, picking the u that minimizes the DMC energy, exploiting that variational property. And then if we look here, we see, we start at initial high energy and we very quickly, over maybe 100, maybe 200 if I'm generous, 100 steps, propagate down to start sampling the ground state. And then we bounce along sampling the ground state energy. And I didn't plot the walker population on this plot, but this is all stabilized by this point. There's about 3,000 of them in this run. And for the actual statistics to get the energies and charge densities to enough accuracy for the science, there were 8,000 steps done overall. So the run continues significantly off to the right here. But nevertheless, that was very much like the cartoons that we were showing earlier. What now about something much more ambitious, and you don't certainly need a supercomputer to run this. So this is 500 atoms of bulk nickel oxide, so a challenging charge transfer insulator, 6,000 electrons. But if we zoom out, it looks very similar to what we just had for vanadium. So we have energy against step, and here the DMC energy is in blue, so we have this initial propagation down. And I was very generous in the equilibration in this run. And at some point, we start sampling statistics, and you see again where the population, sorry, the DMC energy is bouncing around its average. And I've also plotted the population in orange. And I'll note that during the formal equilibration part of the run, the population is controlled quite strongly to stop it from exploding, becoming too large, and causing us to run out of memory, for example. So this is quite strongly controlled. And so we can't use these statistics. And then when we've equilibrated enough and reached some sort of average, some sort of long-term average, we'll then relax, let the population fluctuate. And you see here it's about 150,000 or so. But still, certainly from the same family, as the vanadium result. And I'll note here, if you plot your own diffusion Monte Carlo energies and you don't see the stabilization, you see something shooting up wildly or shooting down, then that tells you that there is some issue with the trial wave function or something like that. Additional attention is needed. Now, one thing I mentioned, this is a key difference from variational Monte Carlo, is that we now have a time step error. We need to have sufficiently small time steps. And there's very straightforward approaches to treating that. First of all, one way to do this is to extrapolate properties to zero time step. So what we do is a series of runs here, like 0.02, then 0.01, and progressively smaller time steps, and then extrapolate to zero time step. And this paper on bulk silicon has a very careful analysis of all the systematic biases in the calculations and making sure that they are made small enough in order to extract the true thermodynamic properties. So that's silicon. Here's some earlier work looking at, this figure is for zinc selenide. And there's a couple of different ways of evaluating the Schütte potential that we'll be covering in the next session. But if we look at this result in blue, this would be the preferred algorithm. We see that you can do a reliable extrapolation from these sort of 5 or 6 points that are being computed. And they started with 0.06 and worked down to 0.01 or maybe 0.05 or so. So larger time steps than done for the silicon. This larger scale, of course, is helpful because as you do ever smaller time steps, it takes you how you have more cost in order to get the same error bar. So then how might we map these practically to computers? What do the codes do? Well, it's very straightforward. I'm sure you've all sort of realized how this is going to work. And fortunately, it's very efficient. So we can use the largest machines if needed. What one does is put this on a population of walkers spread across all the CPU cores that you want to run on, or potentially put many on one or more GPUs. And so that's sort of shown here. We have many walkers and they're taking their steps, and we have these noisy energies running. Now, this is a little bit more involved than the variational Monte Carlo because due to the need to do the population control and that normalization, there's actually communications every single step in this calculation. And another thing to note is that it's important to have a reasonably large population given the size of the machine you're running on to avoid a load imbalance. And just a simple example here, if we had 4 CPUs and 5 walkers, we would have 1 on the first 3, 1, 1, and 1, and say 2 on CPU 4. And that means the first 3 would have to wait half the time for the 4th CPU to move its 2 walkers compared to their 1. And that's easily solved by having a lot more walkers. So that's also another reason to have a large population in diffusion Monte Carlo. So where does that bring us in terms of accuracy on real world calculations? So here I'm showing some examples for both variational Monte Carlo and diffusion Monte Carlo, building on the availability of energy minimization. So that algorithm sparked studies of many of the quantum chemistry test sets, for example. And the point is, if you work hard enough, and you may have to work quite hard, but if you do that, you can get to chemical accuracy of 1 kcal per mole, or is quite close, with a lot of multi-determinants. So what's shown here is the atomization energy for, I think, the G1 test set. There's a couple of papers on there, this topic around this time with very similar conclusions, fortunately, done by different people with different codes. And let's look first at the diffusion Monte Carlo. So this is the initial single determinant result. Here's more determinants. And you see if you work hard enough and even do an extrapolation, you get below 1 kcal per mole. That's what these authors did. Variational Monte Carlo actually starts out much worse for atomization energies. So this is over 10 kcal per mole. So that's quite poor. But then as you work harder, you will gradually get better and better results. Let me jump to the far right now. If we look at density functionals, well, obviously you can get what you want here. They didn't have access to some of the modern meta GGAs, which would probably be, just a few kcal per mole, but of course not the systematic improvability. If we look at coupled cluster, if we sort of naively do coupled cluster, we see, yes, that will get close, but really you need to do these F1-2 type methods or some extrapolation to really get super accurate results. Or the QMC needs even more determinants in these test sets. Let me show some solid state calculations. And when I was preparing for this talk, this was an existing slide I had, and I initially thought to put in some newer results. I showed some newer results last session, but then I thought, actually, I'll keep these because while these calculations were, relatively ambitious at the time, they are now, of course, much more affordable and approachable. I won't say every day, but they are much closer to everyday calculations that can be done, certainly on departmental resources now, and not need huge supercomputer time. So this first set of studies, now this is bulk materials we're looking at now. This is done by Juan Santana in 2016, 2017. This is looking at the properties of binary oxides that go into, obviously, cuprate superconductors. So calcium oxide going through to lanthanum oxide. And first on this y-axis, this is the error in the formation enthalpy. And we see that diffusion Monte Carlo is doing well here. It's got maybe a few percent worse. And for the different density functionals that were picked, the errors are much, much larger. When one looks at the lattice constant, we again see that the diffusion Monte Carlo, and this is done with the single determinant recipe I've been pushing, we see that's actually very, very good for calcium oxide, but by the time we get to lanthanum oxide, we can see a growing error. It's still maybe only a bit under 1%, but nevertheless, we should note that it's growing probably with atomic number here. And although I don't believe there was any follow-up work done to pin this down, there's really only two sources. There's the nodal error, and then possibly the Schütte potential choice. And as we'll be hearing on Tuesday, there's actually better schemes for constructing Schütte potentials now than were available when these calculations were done. So that could be part of the difference here as well. It was also realized that a particular sweet spot for these algorithms that I've been describing has been looking at 2D materials and bilayer systems. And here, this is a study of the binding curve for bilayer phosphorine done in diffusion Monte Carlo. You can see lots of points with very good error bars here. And then also to look at the charge transfer, because actually this turned out to be a case where the story from the more accurate many-body QMC method was actually a bit different from what diffusion Monte Carlo, from what density functional theory was telling us with the functionals available at the time. And this continues to be very relevant in terms of heterostructures for bilayer materials and also systems such as twistronics. And finally, this shows an example of trying to calibrate or find the best density functional approximation for a given system using DMC. And so this was a study of liquid krypton, where it's certainly not obvious to me which density functional approximation would perform best. And what was done was to do an MD calculation with DFT and then take a few configurations from it, about 20 by the looks of it here. And then, so that's this black line here. This was LDA from configurations from the DFT calculation. And then simply compute the energy of those with diffusion Monte Carlo. And we see there's not a good correspondence here. But these authors, they use another functional, the AM05 functional. And we see a much closer track of the DMC results. And then presumably one could keep doing this sort of self-consistently or try ever more functionals. And this is, of course, a way to find the best fit to the data that one has, One, of course, has to hope that there is a density functional approximation that will give a really good match to the QMC results, because that's actually not guaranteed. We've seen some magnetic bilayer systems, for example, where you really have to choose between the geometry and the energy, for example. But here, clearly, this is a better choice than using LDA. So that was a lot of introduction and some examples. Let's now talk about some comparisons of the pros and cons and get into some more of the practicalities. So here I've got advantages and disadvantages, and I've also pulled out the errors and approximations because, of course, we have more of them than compared to VMC. So what are the advantages? So first of all, DMC gives very accurate and robust results, even with actually surprisingly simple trial wave functions. So that's really why it's the workhorse method for systems of not just hundreds, but even thousands of electrons. It's systematically improvable through better quality trial wave functions. And importantly, it also has a good mapping to the current computers we all have access to. So that's on the plus side. On the minus side, something to note is that we don't get an explicit copy of the trial wave function. And so that means measurements are more difficult, and there is something called the mix estimator problem for properties that don't commute with the Hamiltonian. And there's some tricks to deal with those, but it's just much more involved. DMC is more expensive than Variational Monte Carlo. One reason for that is we have to take many smaller time steps. We also have to measure the energy every step in order to actually perform the DMC algorithm, which is not required in VMC. And you'll also see here, as you go to higher atomic number or effective atomic number, the time step also needs to be small. So these work to push up the cost. As before, when one is looking at periodic materials, one has to construct supercells and do finite size scaling. So that adds up to the cost compared with, say, DFT, where one can just study the primitive cell and rely on k-point sampling because it's essentially a mean field method. In terms of error and approximations, we should note the most important approximation or error is the fixed node error, which is variational in the energy. We also have to remember to make sure we test the time step. Otherwise, we'll have a bias coming in and either do extrapolation or just make the time step small enough that the relative errors in properties are well enough converged. And finally, as we'll be hearing, non-local shooter potentials need some special treatment, and there's standard approaches for those that work very well, but we'll be hearing about those on Tuesday. So that's the end of my section on diffusion Monte Carlo. Let me now talk about some practicalities. So now let's look at the overall QMC workflow. We've essentially added a block at the bottom. So what we're going to do is we're going to generate the terminal part of the trial wave function using large basis set DFT calculation or quantum chemical calculation. I'm recommending here we start with one determinant. We then choose a Jastrow function, we optimize it, we then do maybe a longer VMC calculation, but once we have the trial wave function, we can then do production diffusion Monte Carlo calculations. And then much more importantly than for VMC, the first time we do a system, we've got to come up with a plan to test a few different time steps. So I apologize for all the text, but this is a question that regularly comes up. There's obviously a lot of flexibility in these methods, and the question comes, how do I choose? And what I would really highlight is that all of the choices that are being made in these methods are testable because we have variational principles to fall back on. So for example, if one's wondering, is my run long enough? Do I have enough steps? Well, you can simply run longer to obtain better statistics and just reconfirm your statistical analysis still holds. If one's wondering about whether one has enough configurations in the optimization to get the best wave function, one can do, and this is something we'll be recommending, you can do another run with more configurations and see if that makes a meaningful difference. If one's worried about equilibration, one can simply run a bit longer similarly. And then ultimately, one can do independent runs and verify the results agree to within error bars. And of course, if one does that and they're truly independent, that's a very robust result that you have there. This may seem like a lot to test, but actually the statistical properties are given by the quality of the trial wave function and also, for example, the atomic species. So once one has done an example of one class of system, the same properties are going to hold for small variations away from it, right? So if you run some long chain alkane and make a small change to it, all the same statistical properties are still going to hold. Now, we talked through a little bit of rough guide, sort of every, this has definitely got some of my biases in it. In terms of some of the settings that one can use in these calculations. And obviously my biases come from the kinds of molecular and solid state calculations that I regularly run. But I think these are really representative of what people are using in the field and many published calculations. And I'm giving this here just to provide some rough guidance for what you might put in your input files. Because if they're a factor of two difference, no big deal. If they start to be orders of magnitude difference, I would suggest you need to take another look at the run carefully. So in VMC, time steps might be about half an atomic unit. The warm-up is very quick in Variational Monte Carlo because we don't need to measure the energy or any other properties. We just keep moving the electrons. And that may be 100 steps, but you could put 200 or more there. And since VMC is so quote unquote cheap, that doesn't actually cost you much time. We'll be talking about statistical analysis in the next session, but one thing to note here, this is going to be a contrast with diffusion Monte Carlo, is that the correlation period, which is the time between, or the number of steps we have to move to get truly independent measurements of particular properties, that correlation period is quite short in Variational Monte Carlo, maybe only a couple of steps. How many optimization samples to use? I like to start at 10,000 and perhaps grow from there, although I see in the literature many people start with a few thousand. And then since I mentioned this blocking strategy, having many blocks helps with having a robust analysis of the statistics. Now on the diffusion Monte Carlo side, and this is a key point here, the time step is going to have to be much smaller, say 0.01, both for accuracy and stability. The cool down, or it's called a warm-up, or move to equilibration, that propagation down to the ground state might take 100, 150, 200 steps, or about an atomic unit if one multiplies by the time step. And the Walker population, should be in the thousands. I see people publishing in very good work in the thousands. I might start at 10,000s, and we'll be hearing some considerations about GPU usage later in the school. Important point to note, and this is part of what contributes to diffusion Monte Carlo's relative expense, is that because of these small time steps, each new configuration is very similar to the old configurations, and so it might take 100 steps to get a statistically independent sample, much slower than in Variational Monte Carlo. Some quick notes on wavefunction quality, and this will be tested in some of these examples, but I want to include a little bit of this today. And of course, these are all testable. Take a single determinant starting point. What about basis sets? Well, we support both Gaussians and periodic plane waves or splines for periodic boundary conditions. And for molecular calculations, the basic message here is use the largest basis set you have access to and can afford in the SEF calculation. So that might be a triple zeta calculation, for example. It's very much a false economy to use a small basis set on the cheap quantum chemical calculation before doing the more expensive diffusion quantum Monte Carlo calculation. And I'll note in periodic boundary conditions, the potentials that we'll be describing, correlation consistent effective core potentials, are very hard, which means they need a lot of plane waves, maybe 100 Rydberg, maybe 300, maybe 500, which is a lot more than perhaps the 50 one is used to using with conventional ultra-soft potentials, possibly even a smaller value. So that's important. Otherwise, you'll just have a much noisier wave function as a starting point than you really need to. There's a very nice example of basis set dependence in Matistubetsky's chemical reviews paper. And this is energy against basis set. So there's a bigger basis set as we go to the right. This is Gaussians for the HF dimer, hydrogen fluoride. And this is the coupled cluster result with a small basis set result, with a small basis set. So we see that it's quite high. And then as you add more basis functions, it gradually gets lower and improves. Whereas if we now look at the fixed node diffusion Monte Carlo results, you see that actually the coupled cluster is tending towards the diffusion Monte Carlo result, but the fixed node diffusion Monte Carlo result has got a very weak basis set dependence. There certainly is one, but it's really very, very minor, and one could actually use quite a modest basis set by comparison. So this actually shows the importance of doing basis set extrapolation in quantum chemical methods, and there's not much need for it in fixed node diffusion Monte Carlo because the basis set sensitivity is just much, much lower. Just a note on accessible system sizes, and again, this is very subjective and a little bit hand-wavy, but this is a question that has come up in the past, so I wanted to address. And this is sort of based on sort of typical error bars of 0.1 eV or so on things like formation enthalpies, which is often enough to do the science we're after, like work out which a phase of a material will be more stable, for example, because this is already better than typical density functional approximation error on a system where we don't have a lot of calibration data. And so what I would say is, if you've got up to maybe 100 electrons, maybe 150, if you've got a modern, really strong CPU node, you can definitely run some molecular calculations there or some solid state calculations of quite some size. Certainly many of the older calculations I showed would fit on this. Of course, if you want to then look at many molecules or many solids, it's helpful to have some small departmental cluster. And I know, several assistant professors who've got a small cluster that they got with their startup money, or perhaps their physics or chemistry department has a small cluster. And that's already plenty for the majority of calculations that I showed in this talk. And then finally, of course, if you have, I put here like 500 electrons, or alternatively, if you want a really small error bar, yes, it's really worth having a supercomputer time. The point I wanted to make here is that, of course, yes, the calculations become more expensive as the electron count goes up, but there's a huge amount of science that nowadays fits on very accessible computational resources. So I'm beginning to wrap up now. I want to point to some of the topics that we didn't cover. So this will then become known unknowns, and we can ask questions about them, or point you to materials that we might already have on them. For example, I didn't speak about excited states, but we've actually got a very good lab and tutorials on excited states. So topics I sort of skipped over that we'll be covering later sessions: statistics, shooter potentials, and periodic systems for doing solids and finite size effects. I haven't spoken here about advanced wave function forms, be they not just multi-determinants, but backflow or perhaps neural networks, to really focus our discussion on sort of the standard recipe that is very effective for research in the field. Of course, there's a lot of observables that one can compute. So I know someone is interested in density matrices, for example, and we should have a discussion about them. We're very much focusing on energies here. I mentioned the mixed estimator problem. There's workarounds for that. And there's also quite a few other flavors of quantum Monte Carlo. And if someone is particularly interested, yes, we should have a discussion in the chat over the coming days. The reason really for focusing on real space quantum Monte Carlo here is that it's really the method that has proven it can scale to hundreds of electrons, thousands of electrons, and look at systems of good complexity, and then do interesting science problems, move away from just doing benchmarking. Of course, all of the methods I've shown here are all growing, but it's the real space QMC that's been really running at scale. And of course, all of these methods are improving. So last slide before moving to any questions. So I spent my time here outlining the two main workhorse methods, variational and diffusion and quantum Monte Carlo. And these, of course, have got different properties and are quite complementary. So first of all, variational Monte Carlo is our starting point. It's the simplest. There's no approximations in it besides the choice of a trial wave function. The corollary, of course, is that it places all the emphasis on the trial wave function. So one has to do a good job there. Diffusion Monte Carlo is more powerful and more accurate, but also the cost is much higher. And as I was just describing, it has a few more limitations. So I hope that was an effective initial overview of these different quantum Monte Carlo approaches and will sort of help set the foundation as we move into more practical applications of these methods. Next session, we'll be studying shooter potentials, workflows, and statistical analysis. And now let me open it up to any questions.
Yeah, Paul, we have first is a very quick question from Malana. She's asking for variational Monte Carlo, but the question is general variation Monte Carlo or diffusion Monte Carlo. Is the random seed changed performing a random walk in each CPU unit?
So that's a very good question about the use of random seeds and random numbers. Okay, I'll look at the diffusion Monte Carlo one. So of course, we want all of these walks to be different and to get as much statistically independent data as possible. So there's a procedure to ensure that all the random number streams that are going to be followed on every CPU for every walker are different. That's based on an initial seed that the user puts in, but then that gets transformed in a way to seed the random number generators so that they are different on every CPU, different for the evaluation and moving of every walker. If we didn't do that, these plots, say for CPU 1, would look the same as for CPU 2, and we'd have a much less efficient simulation.
Yeah. So I just want to add a
Yeah.
comment. Yeah, so ours random generation is called pseudo random generation. Once the seed is fixed, the sequence is fixed. So if you started with the same seed, then you just replicate the statistics, which doesn't help so-called ergodicity. That's why we try to spread the seed. However, each walker, its calculation supposed to be statistically uh, kind of sufficient. So QMC is not very sensitive to how you exactly select the initial seed. So users should not be that concerned about how we select the random seed to initialize.
Actually, that's a very good point, Yi. We don't actually use that many random numbers in these calculations. So although that can be concerned about the use of pseudo random numbers, we don't use that many compared to some very high accuracy other applications. And so the main thing is, yes, you can specify an initial seed, so you have reproducibility of the runs, but then there's enough steps taken to make sure that different sequences are used for every compute core.
Okay. Second questions is from Saransha. Uh, so her questions are below. Why does variational Monte Carlo workflow in QMC rely on DFT or Hartree Fock orbitals obtained from a large basis set, even though VMC itself is a real space wave function method? It feels like a contradiction to me. Um,
Okay, so I heard the question about why use large basis sets for variational Monte Carlo. Is that correct?
yeah, I think maybe I can help breaking the question
Mhm.
into a few smaller ones. Okay, first question is why we take for variational Monte Carlo, why we take wave functions from DFT method or Hartree-Fock method?
Okay, so that's a great question. And the answer is simply that
Mm.
empirically, it's been found to work very well. So the charge densities that come from those methods is quite good, and the sets of single particle orbitals are quite good. Let me see if I can find, yeah, this example. Um, and so there's a lot of papers seeing, how accurate VMC and diffusion Monte Carlo is using different sources of trial wave function, because it's obviously of interest to use the simplest possible scheme in order to have an accurate trial wave function, because that could save a lot of time. And so what one sees here for this particular test set, just taking single determinant here the first diffusion Monte Carlo, was that the error was 3 kcal per mole. So the nodes are quite good in this scheme. Now we see here that the wave function for this test set, single determinant in Variational Monte Carlo, was much less good, and it took quite some work actually to improve it. Now, why take a large basis set? There's an important point here, and that is even though the uh, basis set convergence, let me see if I can find this. I forget where it was. Here we go.
Mm.
Um, so this is the plot for HF from Mr. Stubetsky's paper, and in fixed node diffusion Monte Carlo, we see that the basis set dependence is quite weak. But there is a little bit of dependence. And this is just for the energy, and of course, perhaps for other properties, it could be more or less severe. I don't think it will ever be particularly severe. But the issue here is that in real space quantum Monte Carlo, the electrons are being moved around in the Monte Carlo process, and they won't only go on the high density regions really close to the atomic cores. Every so often, one will go to a low density region in the tails of the wave function. And so having some basis functions out there is important in order to have a good quality trial wave function, because while it may not contribute much to the energy, that might contribute more to some other properties. I'm thinking of the dipole moment, for example. Perhaps that's a bit sensitive. So it's definitely worth using a large basis set. But as you can see here, one doesn't have to work anywhere near as hard as in other methods.
Yeah, I think so the basis set impact, just adding comment, basis set impact on VMC and DMC is different. VMC is a variational method, so it's bounded by the basis set you choose. As Paul has shown in this slide, DMC, you can view it as an infinite basis set. The projection mechanism can actually go beyond the limitation of the input basis set. That's why you see on this curve, the red curve, that the basis set impact is relatively minimal uh, in diffusion Monte Carlo. I think her question, there's a little subtle second aspect because she's asking about numerics. So she's mentioned that VMC itself is a real space wave function method, while we talk uh, orbitals from Hartree-Fock DFT, they have a basis set. So why we are bounded by the basis, like where this basis set story connects numerically?
I'm not sure I fully understand the question, but uh,
Maybe,
we're
maybe I can,
we're seeking to set up
yeah,
the most accurate single or many determinants that we can, and so the orbitals in those determinants. And I'm afraid I don't have a formula showing the determinant expanded out with with the orbitals in it. That obviously needs to be uh, well represented. So, for example, in the tau regions that I just explained. And so, but we do have a choice in basis set.
yeah.
So actually one area is where real space quantum Monte Carlo has an advantage is we can have many different basis sets. So I mentioned here using Gaussians to expand the wave functions, but one can also use plane waves or just have points on a grid and interpolate them. Um, so I mean, that's still a basis set, although it's not a finite basis set in the sense that a local, like a LCAO type approach might be, and it still needs converging in order to get the tails of the wave functions well represented. And this is actually important both in molecular systems, but also if we're looking around a defect or a vacancy in a material, it's useful to have some either basis functions or real space grid points or plane waves out in interstitial regions, because that's where some of the physics lies, where some of the changes in charge density that would contribute to the formation energy of that defect or that defect's properties come from. But we have some choices here. And if when we wanted to add wavelets, for example, we could certainly do that.
Yeah. Yeah, QMC is very flexible on what exactly basis set it use. It's just a numerical choice, mostly for efficiency or for all kind of consideration take into account.
Yeah.
Okay, so next is a hypothetical question. If we would run DMC with Hodge-Fock tri-wave function without Jastrow factors, let us suppose this DMC calculation smoothly converges. Does it converge to the CBS limit of foreseeable value given by the used basis set?
Okay. Now let me repeat that back. So the question was, if we do diffusion Monte Carlo with what I think is a single determinant of Hartree-Fock orbitals, is that going to converge smoothly to the full CI complete basis set result? And the answer is no. So there's 2 points here. First of all, if you run diffusion Monte Carlo, and I'm afraid don't think I've got a relevant slide, so I'll just have to talk. If we run diffusion Monte Carlo with let me go back to the trial wave function, that might help. So if we have a trial wave function which is just a single determinant, and it doesn't have these additional correlation functions and physics built in, we can of course still run, but we probably won't have the cusp of the wave function accurately reproduced. We'd have to be very careful in the basis sets, actually referring to the previous question, used to get that right. So what that would mean is that we would have a quite noisy diffusion Monte Carlo run compared to what we'd have if we put even the simplest of Jastrow factor, just the minimal one, to fix up the cusp condition. But that would work, and that's actually a test that one can do. It's not very practical for doing science because there's much more efficient routes to do, but that would work. But now we have to ask ourselves, what energy would we get? Well, the energy that we would get would be the energy given by the fixed node error that comes from the Hartree-Fock nodes, not the same nodes of full CI in the complete basis set limit. So the error would be, positive because of the variational principle of diffusion Monte Carlo. How much higher would depend on details of the particular system. And let me find that example of molecular systems. So we know, it wouldn't be perfect because we see here, one determinant, and maybe this was B3 ellipse nodes. I forget in this particular paper. There's another one around the same time that does actually, I think, check this question with Hartree-Fock nodes. We see we have to add lots of determinants to get towards even chemical accuracy. And so, of course, the full CI CBS limit, if it was even achievable for these systems, is, of course, 0 on this plot. So actually, none of these methods shown here can practically get to that for the G1 test set.
Okay. Hopefully Zoran can get some insight from those figures. He has also another question about the size consistent error. Are these size consistency errors associated with the separate optimization of the tri-wave function for the composite system and their fragments? If exists, does it translate to the binding and atomization energies?
Okay, so this is an excellent question about size consistency. And this is a more technical issue, but the question is, if the issue that rises, if we do systems of different size, do we get consistent accuracy and consistent errors? And that actually depends on the construction of the wave function. And I want to say Claudia Philippi has got a very nice article analyzing the case for one particular class of wave functions. So I will try and dig that out and put that on the Slack later. So it depends is the answer to the question. It's not large, I would say, with typical wave functions, but it's not guaranteed to be zero. One has to be careful in the construction of the wave function. Any more questions, or
That's the question
have we exhausted them?
I don't have new questions so far.
All right, maybe we'll wrap up here in that case. Of course, by the way, these are all excellent questions. Please keep asking more on the Slack, and we'll get to them, later today and over the coming days. So thanks all for coming to this presentation, and I look forward to seeing you at the next session, which will be on Tuesday. Thanks all.